Well, hi there. Okay, so today we are going to talk about kinematic equations and kinematics in general. And I'm going to give you two ways of solving all the problems. One by drawing a velocity time graph, and one by doing using your kinematic equations. So let's go ahead and start. So a car has an initial velocity of 30 miles per hour. It accelerates at 2 miles per hour per second for 10 seconds. What is its final velocity? So one way to go about solving, let's see if I could draw straighter lines there. Solving this problem is through a velocity time graph. So time is always on the horizontal axis. And so let's do time in seconds, and we'll do the velocity in miles per hour. And we start at 2 miles per hour. Excuse me, not 2, 30. We start at 30 miles per hour, accelerates at 2 miles per hour per second for 10 seconds. So this is our acceleration. Acceleration is 2 miles per hour per second for 10 seconds. So this is 10 seconds. And so that, we want to know the final velocity up there. Well, if we know that this is 10 and that the slope is 2, then we could find, then we know that this is 20 because this raises 2 for every one it goes over. So if the change is 20 miles per hour and we start at 30, then we know we end at 50. So the answer is 50 miles per hour. We can also reason it out, and we could say that it accelerates 2 miles per hour for 10 seconds. So after 1 second, we've gotten 2 miles per hour faster. And after 2 seconds, we've gotten 4 miles per hour faster. So if we go 10 seconds, we know that we have gone 20 miles per hour faster. So if we start at 30 miles per hour, and we got faster by 20 miles per hour, then we end at 50 miles per hour. We could also use the definition for acceleration. Acceleration is change in velocity over change in time. And that is Vf minus, you'll see it written as Vi or V naught. It means the same thing. It means the initial velocity over change in time. If I multiply both sides by change in time, acceleration times change in time is equal to Vf minus Vi, and then subtract Vi or V naught for both sides. Acceleration times change in time, add it to both sides. Vi naught is equal to Vf. We get our first kinematic equation. This is our first equation right there. Vf equals Vi or V naught plus a change in time. So let's try another problem. A child slides down a constant slope on a toboggan. When the child passes her older brother, he estimates her speed at 2 meters per second, and when she passes her younger brother, 10 seconds later, he estimates her speed at 10 meters per second. Estimate how far apart her brothers are standing. Now, let's see. So let's draw a picture of what's going on. So here's a slope. I'll get a toboggan here, which is usually our those fancy red sleds. Draw the little girl. She has like her head on. There we go. There's a little girl. She'll be sitting down here as well. Okay, alright. And her brothers. Estimates her going at 2 meters per second. estimates, rather. Very good estimators, by the way. Estimates are going at 10 meters per second. Okay, so again, let's draw a velocity time graph. Velocity time in seconds, and velocity in meters per second. So the initial velocity is 2, and the final velocity is 10. And the change in time we're given as 10 seconds. Okay, so here is the key. As you remember from last year and probably from calculus, the area under a velocity time graph is equal to your displacement. So area under a velocity Okay, so in this case, you can either know the area of a trapezoid off the top of your head. I like to do triangles or rectangles, so I break it up into 2 areas. So area 1 is a triangle, so it's 1/2 base, which I'll call 10 seconds, times the height, which is from 2 meters per second to 10 meters per second, so that's 8 meters per second. So, it's 80, 1/2 of 80 is 40, and seconds cancel out, so we have meters, which is good because we're looking for displacement. And area 2 is just a rectangle, so it's base times height, so it's 10 seconds, and the height is 2 meters per second. So this is 20 meters, so we add them up, we get 16 meters total. Yay! Okay, so that's one way to go about solving this problem. Let's look at another way. You could ask, what is her average velocity? So her average velocity, V average, is equal to Vf plus V naught divided by 2, since the acceleration is constant. It's also equal to the total displacement over the total time. So that is the definition of velocity. So if we simplify this, or just make it a little bit prettier, Vf plus V naught, and then multiply both sides by change in time, we get our second kinematic equation. Then we can plug in 1/2 Vf, her final velocity was 10, plus her initial, which is 2, and the change in time was 6 seconds. So 26 is 120, 22 is 60 meters. Yay! Cool! So, we have our 2 kinematic equations, the first one and our second one that is from the average velocity. They're shortcuts. Okay, so, problem number 3. The boat is cruising at 3 meters per second at time equals 0. Ooh, shoot. Okay, at time is equal to 0, the boat begins accelerating with an acceleration of 1.6 meters per second squared. How far will the boat have traveled 10 seconds later? Okay, so again, we can draw a velocity time graph. In seconds and velocity in meters per second. And so it begins cruising at 3 meters per second, and then it has an acceleration of 1.6 meters per second squared. How far has the boat traveled? 10 seconds later. Okay, so we want to find this area under the graph right here. So if we want to find this area, we can find area 1 or area 2 down here pretty easily, 3 times 10. But area 1, we need to know this height right there. So we need to look at the acceleration. So we know that the acceleration is 1.6 meters per second squared. And that's our slope right there. If we know that we go 10 seconds, then our change of velocity is equal to 16 meters per second. So if we start at 3 and we increase by 16, we're going to end at 19 meters per second. Okay, so now that we have this number here, we can solve for the areas. And we'll go ahead and do that quickly. So area 1 is 1/2 the base, which is 10, times the height, which is 16. So that is equal to 80 meters. Area 2 is equal to base, which is 10, times height, which is 3, which is 30 meters. So all together it's 110 meters. Okay. Now let's solve it using the equations that we had before. So we are given VI of the boat was 3 meters per second. We're given that the acceleration is 1.6 meters per second squared. We're given that the change of time is 10 seconds. And we want change in x. Well, we're given VI, A, and change in t, so we can find VF, but we want change in x. And to get change in x with the two equations that we have right now, we'll need VF. So we can solve for VF and plug it in, which is essentially what we did with the graph anyway. We solved for the final velocity, which happened to be 19 meters per second, and then we plugged it in. If we take these two equations and substitute this whole equation in for VF, we get our third equation. So we'll have to use both equations. Okay. So we went through and solved this. So if we solve for both, if we substitute this whole equation right here in for VF and simplify, we get our third kinematic equation. Woohoo! Excellent. And we could have just plugged and chugged at this point. Okay. So, if we, instead of solving for VF right here, instead of solving for VF, shoot, okay, there we go. VF right here, and plugging it in down here, if we instead solve for change of times, and then set them equal to each other, and solve and simplified it, we get our fourth and final kinematic equation. Now this chart is going to come in so handy. This chart has all the variables right here: V naught, VF, change in x, A, and change in time. So these are the 5 variables we can know something about. And each equation has 4 of the 5 variables in it. Now notice all the equations have VI. We could make a 5th kinematic equation where we solve two of them for VI and set it equal to each other, and then we could get rid of the VI. But why do that? It doesn't really come up very often, and if we need to, we could totally do it. So, anyway, here's our 4 kinematic equations. On your EP sheet, this one does not show up in your equation sheet. That's okay, we could do without it, but it's handy to have. Alright, so the way that we're going to work this is we're going to write our givens, and we're going to have always 3 variables that we care about. Doesn't matter which 3. And one that we want, and one that we don't care. The one variable that we don't care about goes in this empty space right here. So I'm going to show you how that works. Okay, so let's try this. We'll do it with the kinematic equations way first, and then we'll solve it using the velocity time graph, which is also very powerful too. I want you to learn how to use both. So we write our givens. So we could have A, BI, BF, change in X, change in time. So these are our 5 variables that we can know something about. And again, BI could be B naught. A plane is cruising at 50 meters per second. The plane suddenly begins accelerating with an acceleration of 4 meters per second squared until it reaches 90 meters per second. How far does it travel in this time? So we want change in X, and we don't care about change in time. So now we go to our kinematic equations. Let's go to kinematic, I'm sorry about this, we're going to go back soon. So, we don't care about change in time, so we look for change in time. We look for the one that does not have change in time. Ooh, right. No. There we go. Okay. So the one that does not have change in time is this one. So, we will use this equation, Vf squared equals V naught squared plus 2a change in X. So, let's back. So we have Vf squared equals V naught squared plus 2a change in X. We have 90 squared equals V naught squared, 50 squared plus 2a change in X. And solve for change in X. Okay. 700 meters is equal to change in X. Woohoo! Easy! Yay! Okay. Let's look at a different way to do it. Velocity time graph. Velocity. Velocity in meters per second. Time in seconds. We start at 50, we end at 90. We go for 10 seconds. How far does it travel? So the how far is our change in X, it's our displacement in this case because it is traveling in one straight line forward. And so that is our area under the curve. So if we look at this and we break it up into two areas, 1 and 2, we have our heights, but we don't know the 10 seconds. We'll get there. We have our heights, but we don't know the time. So let's solve for the time. So we know that the slope is equal to 4 meters per second squared. And we know that our change in velocity is 40 meters per second. And we're looking for our change in time. So 40 divided by 4 is 10 seconds. So now we know that this is 10 seconds. Now that we have that, we can solve for area 1 and area 2 and add them up. So just to be complete, let's do this. 1 is 1/2 base, which is 10 times the height, which is 40. So that's 200. And area 2 is base, which is 10 times 50. Which is 500, and added together, that's 700 meters. Isn't it nice when it all comes out perfect? Okay, so I will see you all tomorrow. Have a wonderful night, and happy physics!